Fire is one of the most fascinating and powerful natural phenomena known to humankind. It has accompanied us for hundreds of thousands of years, giving warmth, light, protection, and energy, yet it can also destroy in moments. Although it looks alive, fire is not a living being. It is a chemical process known as combustion, where matter transforms into energy through a rapid reaction with oxygen. If you like this educational content, please like, subscribe, and share the video with your friends. For fire to exist, 3 essential conditions must be met, what scientists call the fire triangle: fuel, oxygen, and heat. Fuel is any material that can burn, such as wood, paper, gas, or oil. Oxygen comes from the surrounding air and is necessary for the reaction. Heat is the ignition source that raises the fuel's temperature high enough for chemical bonds to break. When all 3 elements come together, the molecules of the fuel begin to decompose, releasing flammable gases. These gases mix with oxygen and ignite, producing what we see as a flame. Once the process starts, it becomes self-sustaining. The heat from the flame keeps more fuel above its ignition point, allowing the reaction to continue until either the fuel or the oxygen runs out. Fire is not a substance but a visible effect of energy release. The flame you see is made of hot gases and tiny glowing particles, mostly carbon, water vapor, and other combustion products. The light comes from atoms and molecules that become excited by heat. When their electrons drop back to lower energy levels, they emit photons, tiny packets of light energy. In other words, the glow of the flame is the direct result of quantum jumps of electrons. The color of a flame depends on its temperature and the material that burns. A cooler flame glows red or orange, while hotter flames appear yellow, white, or even blue. For example, a candle flame reaches about 1,000 degrees Celsius, while a gas burner can exceed 1,900 degrees Celsius. In welding torches or pure oxygen flames, the temperature can climb beyond 3,000 degrees Celsius. The fire triangle also explains how to extinguish flames. If you remove any one of the 3 components, the fire goes out. Water cools the fuel below its ignition temperature. Foam cuts off oxygen. Dry chemical extinguishers interrupt the chemical chain reaction itself. No matter the method, the principle is the same: stop the reaction, and the fire dies. From a physical perspective, fire behaves like a living system. It feeds on fuel, breathes oxygen, and grows as it releases energy. Yet at its core, it is nothing more than matter transforming into heat and light. Every spark, every flicker of a flame is a reminder that energy is constantly changing form, from the invisible bonds of molecules into warmth that sustains life and light that defines civilization. When you look at a flame, what you see is only the surface of a far more complex process happening at the molecular level. Fire is a rapid oxidation reaction in which atoms of carbon and hydrogen in the fuel combine with oxygen from the air. The result is the formation of carbon dioxide, water vapor, and a massive release of energy in the form of heat and light. But this simple formula hides thousands of micro-reactions happening every millisecond. The moment a molecule of fuel reacts with oxygen, it releases enough heat to trigger neighboring molecules to react as well. This is why fire sustains itself. It's an autocatalytic chain reaction. The flame's inner structure. A typical flame consists of 3 distinct zones: the dark base, the area closest to the fuel source, cooler and filled with unburned gases; the bright inner core, where partial combustion occurs, producing glowing soot particles that give the flame its yellow hue; the outer layer, the hottest region where complete combustion takes place and gases emit blue or white light. The visible color of the flame depends largely on its temperature and chemical composition. When combustion is incomplete, carbon particles remain unburned and incandesce, creating the yellow color of a candle flame. When there's enough oxygen for complete combustion, the flame turns blue, like that of a gas stove. The hotter the flame, the shorter the wavelength of light it emits. Red is cool, blue is hot. Why fire glows light from a flame is created by atoms and molecules that have absorbed energy. Their electrons move to higher energy levels. When they fall back to their normal state, they emit energy as visible light. This process, known as atomic emission, is responsible for the glow of the flame and its shifting colors. Different elements produce different colors because their electrons jump between unique energy levels. Sodium gives a bright yellow flame, copper produces green, strontium burns red, and potassium glows purple. This is why fireworks burst in vivid patterns. They are controlled chemical fires. The physics of heat and flow fire also behaves according to the laws of fluid dynamics. Hot gases produced by combustion are lighter than the cooler air around them, so they rise. This upward movement creates convection currents, constantly feeding fresh oxygen into the flame and removing combustion gases. It's this motion that gives the flame its characteristic teardrop shape. Remove gravity, and fire changes completely. In microgravity, such as on the International Space Station, there is no convection. Flames become small, perfectly round and bluish, burning more slowly and evenly because oxygen reaches the reaction zone only through diffusion. These space experiments have helped scientists understand how fire spreads and how to design safer combustion systems back on Earth. The nature of energy. In fire at its core, fire is a demonstration of the first law of thermodynamics. Energy cannot be created or destroyed. It only changes form. The chemical bonds within the fuel store potential energy. When those bonds break during combustion, that energy is released as heat, light, and motion. This is the same principle that drives engines, power plants, and even the stars. Each kilogram of wood releases about 16 megajoules of energy when burned. Gasoline releases nearly 3 times that amount. This is why fire has powered human progress. It's one of the most concentrated, accessible sources of energy nature provides. Fire, then, is more than a simple blaze. It's a window into the fundamental behavior of matter and energy. Atoms combining, electrons moving, photons escaping. In the chaotic motion of a flame lies the purest expression of the universe's constant transformation. Fire has shaped humanity more than any other natural force. It was both our first tool and our first weapon, a symbol of life and destruction, knowledge and danger. The ability to control fire marked the moment when humankind truly began to master nature. Archaeological evidence suggests that early humans, such as Homo erectus, were using and maintaining fire over 1 million years ago. It gave them warmth during cold nights, kept predators away, and made food easier to digest. Cooked food provided more calories with less effort, fueling the growth of the human brain. In a very real sense, fire made us human. With the rise of agriculture, fire became a tool of transformation. People burned forests to clear land and used fire to shape tools, harden clay, and later, to melt metal. Bronze, iron, and steel were born in the heart of the furnace. The mastery of fire led to the birth of craftsmanship, technology, and civilization. But fire also taught us humility. Great fires throughout history have destroyed cities and empires. The Great Fire of Rome in 64 CE, the Fire of London in 1666, and countless others that reshaped how humans build and protect their homes. Out of destruction came innovation, the rise of organized firefighting and safer architecture. In the modern world, fire is still everywhere, though often hidden behind metal and glass. Every engine, power plant, and factory furnace is a controlled flame. When gasoline burns inside an engine cylinder, it produces the same chemical reaction that once lit primitive torches. The only difference is precision. The fire is now measured, contained, and harnessed to power machines, generate electricity, and move entire cities. The industrial fire in engines and turbines, fuel reacts with oxygen in a split second. The hot gases expand, pushing pistons or spinning turbines. This process turns thermal energy into mechanical motion, the basis of the modern world. Power stations operate on the same principle. Fire heats water into steam, steam turns turbines, and turbines create electricity. Every time you flip a light switch, somewhere a flame may be burning. Yet the fire that gave us progress also contributes to the climate challenge. Combustion produces carbon dioxide, one of the main greenhouse gases. That's why scientists are developing cleaner combustion methods, such as flameless burning and hydrogen fuel technologies. Hydrogen burns at over 2,000 degrees Celsius and releases only water vapor, making it a potential energy source for the future. The fire beyond Earth in space research, fire takes on new forms. Experiments aboard the International Space Station study how flames behave in zero gravity. Without convection, fire burns more slowly and evenly, revealing new insights about diffusion, flame stability, and fuel efficiency. At the cutting edge of technology, we find plasma, the ultimate form of fire. Plasmas are ionized gases with temperatures above 5,000 degrees Celsius, used in welding, metal cutting, and even waste recycling. Unlike ordinary flames, plasmas are controlled by electricity and magnetic fields. They represent fire's evolution, from a wild element to a precise scientific instrument. The fire of the stars. On a cosmic scale, fire takes its most powerful form inside stars. There, hydrogen atoms fuse into helium under immense heat and pressure, releasing unimaginable energy. This process, nuclear fusion, is the same one that powers our sun. Every beam of sunlight, every spark of life on Earth is the result of a gigantic, continuous fire burning in space. Scientists are now attempting to recreate this stellar fire on Earth. Experimental fusion reactors aim to generate clean, limitless energy by replicating the process of the sun. A new era of controlled fire, brighter and more powerful than anything humanity has ever known. The eternal symbol. For thousands of years, humans have viewed fire as sacred, from the myth of Prometheus, who stole fire from the gods, to the Olympic flame that represents eternal life and knowledge. Fire has always stood for creation and transformation. Even today, watching a campfire or a candle flame can evoke the same feeling our ancestors knew: awe, respect, and curiosity. Fire is energy made visible, the connection between the material and the eternal. It is the perfect metaphor for humanity itself: powerful, creative, and fragile. Controlled, it gives light and warmth. Unchecked, it consumes everything. Fire reminds us that energy is both our greatest gift and our greatest responsibility. Even though fire has been with us since the dawn of civilization, we're still discovering new ways to understand, control, and transform it. At its core, fire is about energy conversion, taking the potential energy locked within matter and releasing it as heat, light, and motion. But in the modern world, the challenge is not how to create fire. It's how to make it cleaner, more efficient, and sustainable. The controlled fire engines and power plants. Every combustion engine is, in essence, a miniature fire chamber. When fuel mixes with air and ignites, the expanding gases push pistons, rotate turbines, and generate motion. Whether it's a car engine, a jet turbine, or a massive power generator, the principle remains the same: convert the heat of burning fuel into mechanical or electrical energy. Traditional power plants still rely on this concept. Coal, natural gas, or oil is burned to heat water, which turns into high-pressure steam. That steam spins a turbine, and the turbine produces electricity. It's controlled fire on an industrial scale. Fire contained, measured, and endlessly harnessed to power cities. But this dependence on combustion has consequences. Every ton of carbon burned produces roughly 3 tons of carbon dioxide, CO2, a greenhouse gas that traps heat in the atmosphere. This realization has forced scientists and engineers to rethink fire itself, to redesign how we burn and what we burn. Hydrogen and the clean flame hydrogen may hold the key to the next chapter in humanity's relationship with fire. It's the simplest element in the universe and the most abundant. When hydrogen burns, it doesn't produce CO2, only water vapor. The reaction is stunningly clean. Hydrogen flames are nearly invisible and can reach temperatures over 2,000 degrees Celsius. They're already being tested in industrial furnaces, aircraft engines, and next-generation energy systems. If hydrogen can be produced using renewable electricity through electrolysis, it could fuel a future where fire once again gives us light and power without pollution. Flameless combustion and plasma technology scientists are also developing flameless combustion, a process where fuel and air are pre-mixed and burned in a uniform reaction zone. This eliminates visible flames, reduces emissions, and increases efficiency. It's still fire, but one that burns more completely and evenly, a quiet, invisible process of pure energy transformation. At even higher temperatures, fire evolves into plasma, the fourth state of matter. In plasma torches and arc reactors, gases are ionized by electricity, creating temperatures exceeding 5,000 degrees Celsius. Plasmas are used to cut metals, destroy hazardous waste, and even generate synthetic fuels. They're a modern, technological form of fire, one controlled by magnetic fields and electrons instead of oxygen and fuel. Fusion, the fire of the future. Beyond chemical combustion lies the ultimate fire, nuclear fusion. Unlike the fire in our homes or engines, fusion doesn't burn molecules, it fuses atoms. Inside the sun, hydrogen atoms combine into helium under immense heat and pressure, releasing enormous energy. This process powers the universe. Every star is a self-sustaining ball of fire born from fusion. Humanity has been trying to replicate this stellar fire on Earth. Experimental reactors like ITER in France and NIF in the United States are building the foundations for controlled fusion energy. If successful, they will create a new form of fire, one that burns hydrogen not with oxygen, but with gravity and magnetic confinement. Fusion could deliver virtually limitless, clean power, redefining what it means to control energy. The eternal flame of knowledge. From the sparks of primitive flint to the roaring furnaces of industry and the plasma fields of tomorrow, fire has always been our closest companion and our greatest teacher. It shows us that energy is transformation, that light and heat are the universal language of the cosmos. When we look into a flame, we are staring at physics made visible. Atoms breaking apart, energy radiating outward, the same process that keeps the stars alive. Fire connects the campfire to the sun, the torch to the reactor, the spark in a match to the birth of galaxies. In the future, humanity's fire will not burn forests or coal, but atoms and light. We will carry it beyond our planet, using plasma drives and fusion reactors to reach the stars. The element that once gave us survival will give us the universe. Fire is not destruction, it's transformation made visible. It is the oldest story of energy, and yet it's still being written. As long as there's curiosity, motion, and matter, fire will burn, in our machines, in the stars, and in the human spirit that keeps seeking light in the dark.